what I want to do today with you is to give you really a taste of the mathematical basics for numerical relativity. So what's actually behind the code in the Einstein toolkit or any other of the other codes that you may be using when you're solving Einstein's equations or generalizations thereof. That said, since I'm giving you a lecture, I actually decided to use my tablet as equivalent for a board. So this will be a kind of a board lecture rather than pretty slides. So let me share my screen here. And yes, let's start. Good. That looks good. And I actually prepared the slides a little bit because in 40 minutes, I can really only give you a taster. If you do want to read up on this in more detail, there are a set of really wonderful books. One is by Miguel Alcubierre, Introduction to C++ Numerical Relativity from 2008. Shibata has a very nice book from 2015. And then there are two books by Thomas Baumgarten and Stu Shapiro, one from 2010, which is very extensive, and one from last year, which is called Numerical Relativity Starting from Scratch, where you really have it's a very short book. You have a lot of analogies to Maxwell's equations. And I think if you're a beginner, if you're a beginning student, this is really the book that I would recommend as a first encounter to the topic before you delve into the details in any of the other literature. Good. The other question is, what is numerical relativity? I think Zach already told you. This is really the tool, the techniques to solve Einstein's equations, potentially coupled to matter, or extensions of Einstein's equations in 3+1 dimensions. So you really want to solve the nonlinear regime of gravity, and we need to use numerical methods to do that because Einstein's equations are a set of 10 coupled nonlinear partial differential equations. Yeah, so that's why we need to put that on the computer. And as I already said in the beginning, the main application, of course, is gravitational wave source modeling, where we want to compute the dynamics as well as gravitational wave emission when we have a compact binary that's very close to merger, where nonlinear effects become important, and during the merger. Yeah, and you've seen really excellent talks about this yesterday. A few more recent applications are actually within cosmology. So numerical cosmology or computational cosmology is a new thing that has started to be developed in depth really in the last few years. And numerical relativity, including the Einstein toolkit, have also been used to look at, for example, nonlinear stability of black holes, something that's called superradiance. People have looked at high-dimensional black holes and black hole collisions. In my group, we are also using the techniques to study the interaction between black holes and light fields that are dark matter candidates. And yeah, so there's a lot of applications beyond gravitational wave source modeling. Good. With all that said, what are actually the main ingredients? So even if you don't get all the details, and we cannot actually go in to all the details, let me give you a little bit of a prescription of what the steps are that you would have to take when you say want to implement a new code, if you want to perform a numerical calculation and you want to understand in more detail what's behind this. So the first thing that you need, of course, is a theoretical model. So this is kind of step one or even step zero. And why do I write this down? Well, today, and in most cases, most applications in general relativity will look at Einstein's equations in 4 dimensions. In d equal 4. So this is what Zach just said. The r mu nu minus 1/2 g mu nu Ricci scalar equals 2, and I will actually look at vacuum spacetimes today just for simplicity, but you would add matter here on the right-hand side if you're interested in that. And why do I say we have to choose our theoretical model? Well, if you remember Masha's talk yesterday, she was talking about dynamical Schoen-Simons gravity, or more generally quadratic gravity theories, where you would have a modification to your equations here, and you would also have a set of equations for additional fields. I'm not going to go into this, so today we are dealing with Einstein's equations. Now, the first thing that we want to do is actually make the time dependence of our space-time explicit, and therefore we will decompose the space-time into spatial hypersurfaces that will be evolved in time. I'll come back to that in a moment. So this is kind of the first step, and this is actually really just geometry, will not depend on the particular model that you have chosen. Good. Then the next step after that, we want to actually take our theoretical model, our Einstein's equations, and make that time evolution explicit. So we will decompose our field equations in spatial and time-like component. Decomposition of our field equations. Good. And if we do that, we will actually obtain two sets of differential equations. The first set is a set of constrained or elliptic type equations. And we will actually use those to construct or solve for initial data. And I will tell you, I hope I have time to tell you a little bit more about this today. Oops, initial data. And the second set of equations that we get are hyperbolic type evolution equations. So that will tell you how our evolution variables are propagated forward in time. Yeah. Good. And then, as I said, once you have these, you want to think about carefully how to set up initial data. That is, if I have, well, my space-time metric and its first time derivative at t equals 0. This is what you want to do. Or equivalently, we will see the 3+1 language in a minute. This would correspond to prescribing a spatial three-dimensional metric and its momentum or extrinsic curvature at t equals 0. Then we also need to think about the formulation of the evolution equations. Oh, okay, sorry. And this is related to the notion of well-posedness that Masha alluded to yesterday, where you basically want to have a system of equations that when you start with some unique, smooth initial data and you evolve that forward in time, you better have still a unique solution at late times that is uniquely determined by your initial data. And we care about that in numerical relativity because we always have small perturbations, numerical errors on each of our slices, and we don't want to we don't want these errors to grow exponentially, because then in fact our simulations would fail. I will not talk about this today, but if you're interested, I have talked about this in the Einstein Toolkit School last year, and it's actually recorded and available on our YouTube channel for the Einstein Toolkit. Yeah, so today I would rather talk a little bit more about initial data because that's the focus of today. So I want to give you a bit of a background here as well. Good. And then the last two items are actually also rather important. So item 6, I label as gauge choices. Here you want to think about how to prescribe your coordinates, how to describe your, for example, black holes in the space-time. And there are two main techniques. Either you say, I have my black hole, I know classically at least that nothing can escape from my black hole, so let me excise, like cut out the inner region. Or the other approach that we are actually using in the Einstein Toolkit most of the time is called a puncture approach, where the black hole is replaced by one point of on the grid that's taken out of the grid. And we have conditions for our gauges for lapse and shift that allow us to have these punctures that represent our black hole move freely along the grid. And doing all that, ultimately, we want to extract observables. We want to make a connection from our simulations to the gravitational wave measurements as LIGO, Virgo, and Kagra. So the last item on the theoretical side is actually extracting observables. And again, I'm not going to go into details here, but observables are, for example, extraction of gravitational radiation. Or you may want to think about local properties of your black holes, the black hole mass, the black hole spin. And we typically do that by measuring their horizons, more specifically the apparent horizon, which is a local in time concept that we can compute at each time slice during the evolution. So these are all the steps that we need to take. And let's get started with a really brief review on the 3+1 decomposition of our space-time. So this is what I listed as item 2 after we've chosen our model. Now we have our 3+1 decomposition of the space-time. And I think I can be rather quick here because both Manuela and Masha have mentioned that in their talks yesterday. So what we want to do is take our 4-dimensional manifold and slice it up into 3-dimensional spatial slices that are labeled by some time parameter. Yeah. So here we want to foliate our 4-dimensional manifold into space-like slices or hypersurfaces. Let me call them sigma with a label T, and the metric on these slices I will call gamma ij. And if I illustrate that, I will take my 4-dimensional manifold and basically slice this up into these spatial slices. I'm suppressing here one dimension, so these are now 2-dimensional slices, and I will evolve them forward according to some time parameter that I will call T. Now, to characterize each of these slices, we have, of course, the stream metric here, which is intrinsic to these slices and measures distances within the slice, like so. So we have gamma ij, and then the coordinates on each of these slices I will just call dxi. dxj. Yeah, so I, j are my spatial indices running from 1, 2, and 3. Good. So that's our metric. Now, the next quantity that we want to introduce is a vector, time-like vector that is normal to our hypersurfaces. Just try to get up a little bit. Yeah. So this is our normal vector, and mu, it's time-like and normalized such that its norm is equal to -1. Good. Now we can actually ask, how can we describe the elapse of time from one slice to the next? And that's encoded in what we call the lapse function. So we typically call the lapse function alpha. You may have also seen people calling it capital N if you're more familiar with, for example, post-Newtonian calculations. But in numerical relativity, we tend to call it alpha. So this is our lapse function. And this describes how much proper time elapses as you go along the normal from one slice to the next. So proper time between our hypersurfaces as measured by an observer that moves along the normal vector. Okay, good. Now, of course, it may not always be the case that the points that you or coordinate points that you have here will always end up just propagated along the normal vector. It may actually happen that your coordinate points that are, say, here on one slice may be shifted with respect to the movement along the normal vector on the next slice. So say we have P here on sigma T and some P prime here, then this displacement would be encoded in what we call the shift vector. And this is usually called beta I. Again, if you're more familiar with the post-Newtonian notation, that would be capital Ni. So here we have the shift vector beta I. And as I said, it's indicates a displacement between the normal observer and an observer moving along lines of constant spatial coordinates. Okay. Good. So one more thing, and I think from the illustration that is already clear, by construction, this shift vector is orthogonal to our normal vector. Good. And now we can actually use this language of having a three-dimensional spatial metric, lapse and shift, to reconstruct our four-dimensional metric. So let me write this down next, just here. So we can now write the metric in the following form. If I have my four-dimensional line element ds squared, my four-dimensional metric g mu nu, dx nu, where mu and nu are space-time indices, so they are running from 0 to 3. And I can rewrite that now in 3+1 language as minus lapse squared minus a shift vector squared dt squared plus 2 gamma ij, and then I have here shift vector beta I dt dxj, and I have my spatial components gamma ij dxi dxj. So if I wanted to write my metric in a matrix form, I would have the following. So I would have my time component up here would be minus lapse squared minus beta squared. I would have my beta I and beta j here, and then gamma ij would be my spatial components of the metric in matrix form. Good. Okay. One last thing that will turn out to be very useful is to realize that the spatial metric, if we actually take all its components, so we just said it's spatial, but we can actually think of that as a four-dimensional tensor. And in that case, it actually allows us to define a projection operator with which we can project out components of a tensor or of a vector onto spatial slices. So that said, you can introduce this projection operator. Oops. And let me call this gamma mu nu, which is composed of the four-dimensional Kronecker delta mu nu plus n mu n nu. And if I now have a four-dimensional vector, say, let me call this v mu, and I want to write it in terms of its 3+1 components, then I can introduce one component which would be the contraction of this vector with the normal vector. Let me call this curly n here. That would be v mu n mu. And I can define the spatial components, so the ones that are projected out with this new projection operator that we just introduced. Let me call this curly v mu and that would just be the projection, gamma mu nu, and then again acting on our full four-dimensional vector v, so that I can write this vector in the end as this curly n, my normal component, times the normal vector plus the spatial components curly v nu. And I'm telling you that because this is precisely the kind of decomposition or projections that we will use later on to project out different components of Einstein's equations, either projected onto the hypersurface or contracted with the normal vector. This is how we will go from the four-dimensional Einstein's equations to its 3+1 language. Okay, before we can do that, however, we have to introduce a concept that's called the extrinsic curvature, and I will just go to the next slide to do so. And this basically tells us the following. So let me just write this out first. The symbol is K ij typically. And here's the question is, if I have my spatial hypersurface, how is that hypersurface actually embedded in my, into my four-dimensional space-time manifold? And to measure that, we can actually look at how a normal vector is propagated along our slice. Well, let me just draw this. Let me suppress two of the dimensions. So if I take my slice here and say I have my normal vector pointing in this direction, and I propagate this along our hypersurface, then you will see that the direction of the normal vector will have changed. And this change in the normal vector is precisely what gives us the extrinsic curvature if you're thinking about it from a geometric point of view. So this is one definition for the extrinsic curvature, where we say this is minus the change in the normal vector, and I'm projecting out here again with my projection operator. Just a note, the minus sign here is actually convention. So if you look, for example, at Walt's textbook, he will give you a plus sign here. The reason why we like to choose a minus sign is that then the direction of propagation is actually forward in time. Good. Okay, so that's the geometric interpretation. You can show that the extrinsic curvature, if you calculate this out, can actually show that this is related to the Lie derivative along the normal vector of our induced or spatial metric. There's a factor of 1/2 alpha here, and we can write this out as a time derivative minus a Lie derivative along the shift vector of the extrinsic curvature of the 3 metric. That is to say, the extrinsic curvature gives you quite naturally a time derivative of our metric. So we can rewrite this as a kinematic evolution equation, where we have the time derivative minus the Lie derivative along the shift vector of our spatial metric. And I will now really focus on its spatial components here. Gamma ij is equal to minus 2 times the lapse times kij. And why kinematic? Well, here we've only used the geometry of our space-time. So there's no information about our theory of gravity of our field equations in here. So it's really just geometry. It's like in classical mechanics, thinking about the time derivative of the displacement vector as being the velocity. So this is here's a general relativistic equivalent of that notion. To get information about our theory of gravity of our field equations, we now have to look at the 3+1 decomposition of the field equations. Yeah, so this is where the dynamics will come in. So this is the next part. So 3+1 split of the field equation. And let me just abbreviate this here as Einstein's equations. And what we will see in the end is what we typically call the ADM or ADM York equations. And this stands for Arnowitz Descent-Misa. Just a little bit note of caution. So even though in numerical relativity, we call the formulation ADM equations, it's actually not exactly the original formulation. So here we will derive a form that involves this three-metric and the extrinsic curvature. The original ADM formulation uses positions and conjugated momenta, but they are related. So yeah, just as a side note here. Well, what we do here, and again, I'm not going to derive those in detail. I will just give you the key points here. We will use a set of equations that are known as Gauss, Kodazzi, minority relations. And in a nutshell, they basically give us relations between the four-dimensional Riemann curvature of our space-time to a three-dimensional, so is it just spatial Riemann curvature of our, so the intrinsic curvature of our hypersurfaces, JKL, the extrinsic curvature that we've just seen, and this also contains Lie derivative along the normal of the extrinsic curvature, which we will see will contain a time derivative of our extrinsic curvature. So this will give us a time evolution equation later on. Good. Now, what we will do next, and this is just the two, I'm skipping the part where I'm also splitting the energy momentum tensor in the interest of time. So let's just decompose now the field equations. And actually, not decompose, I should actually call this a projection because this is really what we do. And the first set of projections is actually a contraction of the Einstein tensor with the normal vector in one or both of its indices. So if we do that, here we will get the following. So the first one is the Einstein tensor, G mu nu, contracted in both indices with the normal vector, and I typically actually have a factor of 2 here, will give us a Hamiltonian constraint. And this written out gives us the three-dimensional Ricci scalar minus this combination of extrinsic curvature, Kij, plus the trace of the extrinsic curvature squared. Since we don't have any matter in the game here, this is equal to 0. And this is one of the constraint equations. So actually, since I promised you this, that we will kind of see elliptic type equations. So if we were to write this out to leading order, this equation would be a Laplacian of our three-metric plus some lower order terms, if you write it in the appropriate way. So this is just very schematic, what we get here. The second set of equations that we get is the contraction of the Einstein tensor with a normal vector in one of the indices and a projection with a projection operator in the other index, usually have a minus sign here. This will give us the momentum constraint, and that is related to a divergence of the extrinsic curvature minus the derivative of the trace of the extrinsic curvature. Just to, I didn't list this up here, but di is a covariant derivative with respect to our spatial metric. And again, this is equal to 0. So this is what we call the momentum constraint. And the other one, this was the Hamiltonian constraint. Good. And in practice, we typically solve these constraint equations to fix some of the components in our initial data. So typically solved for initial data. Good. And The last type of projection is actually projecting both of our indices of the Einstein tensor with this spatial projection operator. So this would be, say, G mu nu, and now we are projecting out both indices. And this will give us a time derivative of the extrinsic curvature. And I'm leaving out all the details here now, but if I write this out, we will get, well, the Lie derivative of the extrinsic curvature, and then we have here the second spatial derivative of our lapse plus the lapse function times, and again, this three-dimensional spatial Ricci tensor, Rij, plus terms that are related to the extrinsic curvature in this particular form. Okay, J, and let me just write for completeness, again, our kinematic evolution equation for the three metric, and this was just related to -2 alpha and the extrinsic curvature. So now here we have our system of evolution equations in this ADM York form. Good. So in practice, these equations are actually not well posed. Remember, I was talking about this well posedness in the very beginning, where I said, if you start with some smooth unique initial data, we want to have a smooth and solution that uniquely depends on the initial data. If you use these set of equations, we will actually see that small perturbations will grow exponentially. And if you analyze the structure of these equations, they turn out to be ill-posed. So we have to work a little bit harder to make them well-posed. And there are two ways of doing this. One approach is to use a different set of gauges or coordinates. So this is what I would usually call generalized harmonic formulation. And this is what was used, for example, in the very first successful binary black hole simulation by Franz Pretorius in 2005. It's also, I think, the basis of the formulations that I used in the SSX collaboration that Masha mentioned yesterday. And the other bulk of formulations go under Baumgarten, Shapiro, Shibata, and Nakamura system. Or short BSSN. And this is a reformulation from 95, 99, where you add the constraints in a specific way to change the character of your equations. And kind of in between those two is a formulation that is called Z4, and there are different incarnations of that reformulation. In the Einstein toolkit, we have both this BSSN formulation and the Z4 formulation. Yeah, so different codes, different code bases use different formulations, and I always find it really amazing and reassuring that when we compare, for example, the gravitational waveforms that we get out of our computations agree extremely well. So it's really a benchmark for all of us using very different formulations, very different implementations in the code. Good. So I'm not going to go into any of the details here, and I see I have about 5 minutes left. So let me tell you in just 1 minute in a bit more detail what we do in practice for the implementation. Because if we look at the set of equations that we have here, we see a structure where we have a time derivative here on the right-hand side and spatial derivative, sorry, time derivative on the left-hand side, spatial derivative on the right-hand side. And that is actually a form of the equation that is very useful for our implementations. So let's think about the structure. So what I just said was that we have on the left-hand side some time derivative of a vector of evolution variables, so say our metric and extrinsic curvature. And on the right-hand side, we have a function of our evolution variables. It's second and first spatial derivatives. And that's actually something that we use when we adopt the methods of line. So this is something that underlies at least the evolutions in the Einstein toolkit, where we can choose one discretization scheme for the spatial derivatives. So for example, we use finite differences most of the time. In the SSX collaboration, or for the spec code, they are using pseudospectral methods. So you have a free choice of what free choice of what you're doing with your spatial derivatives, and you can choose a very different scheme for your time derivatives. So for example, we use most of the time a fourth order Runge-Kutta integration scheme, although the Einstein toolkit actually provides a much larger variety of time integration techniques. Good. And in practice, what we do, we prescribe our initial data on the initial slice by solving the constraints, and then freely evolve that initial data in time. And we only monitor, recompute the constraints at each time slice to benchmark and check our implementation. Good. And we can do that. Maybe let me just write this down. So in practice, we use a free evolution scheme. Yeah, that is, we solve an solve the constraints for the initial data. And freely evolve in time. So, and we just check or monitor the constraints as we go along. Good. Now, Zach, quick question. The time is including or excluding questions?
Just unmute myself. Yeah, so let's see here.
Yeah, because then I will just...
All I'll say is the next speaker is scheduled to start in 7 minutes. So
okay, good. So then let me just finish with a final remark, and I will not go into the initial data construction because that I would definitely need more time for. So then let me just finish here and just add a couple of remarks. So the really brief walkthrough that I gave you here is just a taster. As I said, if you want to learn more, I invite you to look at the references. I also focused on just Einstein's equations in vacuum. So of course you can extend that and you can couple matter to your evolution equations, and you would again think about time evolution formulations for your then meta variables. You would have a contribution of the meta content to your constraints and evolution equations. You can think about coupling additional fields to it. And as we've seen yesterday, the whole formulation becomes much more involved if you go beyond general relativity, and Masha has given you a taster of how you would approach this problem in that case. So, which is to say that numerical relativity is a really powerful tool to solve the strong gravity, nonlinear regime of gravity using high performance computing. And I believe you will see a lot of really exciting examples as you go along in the school in this week. And well, I wish you a great day today and a lot of fun for whoever goes to the LIGO site. I'm really jealous that I can't be there in person. And with that, I will stop here and take questions before the next speaker starts.
Great. Well, thank you, Helvi.
And actually, let me just stop sharing the screen so that you can also see me again.
Yeah, wonderful overview. Yeah, we have a question. Okay, so the question was, how is the generalized harmonic formalism different than what you derived?
Okay, so I didn't really have time to get into that, but basically what you do is that you use a wave equation for your coordinates, a generalization of a wave equation for your coordinates, while so basically we have different ways of treating with terms that mess up our well-posedness. So in the generalized harmonic formulation, you would use these harmonic coordinates, so wave operators for your coordinates that help you rewrite Einstein's equations as a set of wave equations for the metric. In the BSSN formulation that we have in the Einstein toolkit, we realize that by adding the constraints in a particular way, and we also have a different set of evolution equations for the gauge, for the lapse and the shift.
Yeah.
I don't understand the difference between the excision and the puncture method.
Yeah. Could you briefly describe the difference between the excision and the puncture method for evolving black holes?
So in a nutshell, think about having a numerical domain. You have your black hole here. And if you use excision, you're basically cutting out the points inside your black hole. So say you assign it 0 values or some other values, so that you don't have the singularity of your black hole, the divergence on your grid. In the puncture method, we basically realize that by shuffling, so we introduce a new set of variables where we have a conformal factor that contains a singularity, and we basically just extracting out 1 point from the grid. So magically, so we are not actually doing anything to the interior region. It's all going through smoothly, and we're basically taking care of the singularities by adopting a good set of coordinate choices in a nutshell.
Cool. Thank you, Helvi. See, any other questions? Do we see any in chat? Oh, here we go. So Claudio asks, could you explain to us a little bit about pseudospectral method?
Okay, not in much details. I would say to read up on that in a textbook, because we just don't have the time to go in very much detail here. Right, but the main idea, so that the 2 different approaches, finite differences, you would take your grid and you would split it up into a discrete set of points, whereas for the spectral or pseudospectral methods, you're basically writing your equations in the basis of Chebyshev polynomials. Yeah.
Well, I think that's all we have time for. Thank you so much again, Helvi.
You're welcome, and have a great rest of the meeting.